guys through my group project about chemical process in order to produce ammonia. Ammonia is one of the most highly produced inorganic chemical. The production produces tons of nitrogen, ammonia, using for the production of plastic, fibers, explosive, nitric acid. This is the Haber process. We can use this process to produce ammonia. Before the World War I, ammonia is produced by the dry distillation of nitrogenous vegetable and animal products. However, as technology advances day by day, we can now use natural gas and convert them into ammonia through a very complicated process over here used by engineering professionals. As engineering students, we can use a much more simple process as over here. So, today our problem is how can we use mass balance in order to generate various plots to graphically analyze the process, and then we can use this graph to provide recommendation on how to optimize the system. For our known variable, we have the XY0, which is the mole fraction of inert gas in the fresh feed, the FSP, which is a single pass conversion of nitrogen and hydrogen, and the YP, which is a fraction of the gas leaving the condenser. However, we also have the N1 and N2. Because this is a stoichiometric process, we can assign N1 as our mole of nitrogen. Therefore, 3N1 is going to be the mole of hydrogen, and N2 is going to be the mole of processed gas, of inert gas, excuse me. So, for our output, which we want to calculate, is our NR, the total moles fed to the reactor, our NP, the moles of ammonia produced, and our FOV, which is the fraction of the overall nitrogen conversion. First of all, we need to consider the process in order to figure out how N1 and N2 are going to be calculated. So, we have the fresh feed coming in this way, which is contain 1 mole of nitrogen, hydrogen, and inert gas. This mole going to go through a reactor, and this will be our products, which is nitrogen, hydrogen, inert gas, and ammonia. This product going to go through a condenser and coming out these two ways. This way going to produce ammonia, and this way going to produce the remaining 3 substances. At this stage, these 3 substances going to go back as a recycle, and they're going to go through this process again. So technically saying, if we consider this stage, this is our first input, this is our second input, and this is going to be our output, if we consider this stage only. So, in chemical process and in specifically mass balance, we have input plus generation, these two plus generation going to equal to our output plus the consumption plus accumulation. However, this is a steady state which the process variable do not change with time. We can assume that accumulation equal to 0. And this is a mass balance equation. We can also assume that generation and consumption equal to 0. Now, we can calculate N1 and N2, and from that, we can calculate NR, NP, and FOV. So, for the balance equation, we have output equal to input. We can use input equals to output. Our input gonna be the first input plus the second input. For the second input, instead of using these 3 things, we just can use 1 mole. So we have 1 mole plus the first input. For our output, this is our output because input coming this way and this way, so this is gonna be our output. So output is 4N1 plus N2. If we rearrange the equation, we're going to have N1 is equal to this equation. For N2, in order to calculate N2, we need to take and consider that the mode of inert is going to stay constant throughout the whole process. So this is the amount of inner gas going in. This is the amount of inner gas going out. So these two things will be equal to each other. And then we can calculate N2 is equal to SY0 divided by YP. For the NR is the total mole fed to the reactor. So this is going to be the total mole fed to the reactor. NP is the total mole of ammonia produced. So this is going to be our NP. For FOV, we can follow this equation to calculate FOV, which is the mole of N2 fed minus the mole of N2 purged divided by the moles of N2 fed. This is the mole M2 fed, and this is the mole of N2 purged. So now once we have all the equation, we can input it in the user-defined function over here. Now, first of all, before the user input, we need to have a data validation because FSP, SY0, and YP cannot be bigger than 1 because they are on fraction. And we can put the user-defined function over here to calculate what we need to calculate. So, for the second task, we need to keep two of the input constant and change one of the input to see how much the mole of ammonia going to be produced. The first thing is we keep XY0 and FSP constant and we change YP. I use a for loop because it is easier to store the NP going to be produced into a matrix so that we can graph later. So as YP vary from 0.01 to 1 and I initialize A is equal to 1, and as long as this condition is kept, these two are going to be calculated. The smaller A and B is going to be the cell that store each of the NP going to be produced, and A need to be changed by using A plus 1. So smaller A, 1 will store at the first NP, and it coming on A1, A2, and A3. And then I plot the graph because this is because the NP and YP store into each cell. I need to convert into a matrix in order to plot the graph. And since the graph is theoretical, we can use a straight line. The second case, we kept XY0 and YP constant, and we change FSP. We do the same thing of plotting, and then for the third case, we change XY0 and held constant the FSP and YP. So then for the fourth figure, we need to put all of the three graphs into one figure to see how the graph gonna look like. And among all of these three, we need to determine the relationship between NP and the input we're gonna change. For the third task, we need to optimize the system by knowing which variable to change to maximize the whole system. So for the first case, we need to find the max of YP, and for the second case, we need to find the max of FSP, and for the third case, we need to find the max of XY0. By doing this, we can know among of these three which is the max of the max, and then we can know the maximum NP gonna be produced. So the final thing we need to do is testing our code. So I will run this, and if I put anything not between 0 and 1 like 5, they're gonna give me a warning, and I have to input again. I'm gonna input 0.1 for the mole fraction of inner gas. I'm gonna input 0.4 for the single pass conversion of nitrogen. I'm gonna input 0.2 for the fraction of gas leaving, and they calculated over here for all the thing we need when the user inputted it. And I'll run the first graph. So first graph look like this, and this relationship. Then I'll run the second graph. Second graph and its relationship. Then I'll run the third graph. This is the third graph and its relationship. Now we need to run the final one, which is combination of the three previous one. So this is the final graph, which is combining the three previous line. The reason why we can use line because this is theoretical data, not experimental. Now, for the final task, which is just a whole bunch of output statement. So after we calculate which one is the max, we're going to display the output. One limitation of this code is it might only works for 1 mole of the whole thing of nitrogen and hydrogen and inert gas. It might not only works for more than one. And the application, we can use this code to produce NH3 because the code will work for anything that less than 1 mole. So that was both the application and the limitation of the code. So this is the end of our presentation. So thank you for listening to me.